Thank you. I appreciate the opportunity to talk to you about the Arctic system reanalysis. And I'm going to make some remarks as I go along, some of which will be directly relevant to CARRA, and I've got some wrap-up general comments that also apply to CARRA. No great news here, but just from our perspective. Okay, the co-authors are people that have had a major role in producing this regional reanalysis, and we've had a variety of funding from the National Science Foundation, the National Aeronautics and Space Administration, and currently from the Office of Naval Research. Okay, I probably don't need to talk at all about the need for an Arctic-focused reanalysis. Big changes going on with the warming and associated effects, particularly in Greenland, that we're going to hear about very soon. It's a complex system, and so we need to have much better representation of what's happening up there, and of course, things with the permafrost. Okay, so this is our an overview of our Arctic system reanalysis. And the inner domain on the right-hand side figure is the area that we do our reanalysis. So it's much bigger than the initial CARRA 1 and also CARRA 2, which I understand is primarily around the Arctic Ocean. And the reason that we go to the mid-latitudes actually is because we have a broad view of the Arctic, and as far as the low saline surface water in the Arctic Ocean that caps the warm Atlantic water coming in from the North Atlantic is the rivers that flow northward, particularly in Eurasia. Okay, so we looked at 2000 to 2016. It includes the major Arctic rivers and Northern Hemisphere storm tracks in the two major oceans. It uses polar WRF, which I'll describe briefly, and the WRF data assimilation. We used a 3D VAR approach. We spent quite some effort in improving the sea ice specifications. We had two versions, an early version of 30 kilometers, which ran to 2012, and a version 2, which was at 15 kilometers to 2016. So nothing like the 2.5 kilometers that you're dealing with. It has 71 vertical levels. The first level is at 4 meters, so right down in the surface to capture the stratification that is so frequent in the Arctic throughout the wintertime. It's 3-hour output. We use the NOAA land surface model with frequent satellite data assimilation, particularly on the landscape that will become reasons that will become clear in a minute. We used ERA interim for the lateral boundary conditions, and we spectrally nudged to ERA interim in the stratosphere. We've got publications on both of those. Versions are available through NCAR, the Research Data Archive. The reason we have this outer domain is to provide smooth conditions, boundary conditions for the inner domain. So just a little bit about the polar version of the weather research and forecasting model. You should probably know WRF is a very, very widely used atmospheric model. The polar version that we maintain has a lot of users in the polar community. We're about to release version 4.5.1 this month, so we've only got a few days to do that. So some of the key modifications are heat transfer for ice sheets, revised surface energy balance calculation, and we now use the NOAA multi-physics land surface model. You can specify the sea ice cover in the Arctic Ocean, fraction, sea ice thickness, the snow depth on the sea ice, and the albedo. And that's something we developed for ASR, but you have to be able to specify these things. Fraction is obviously the easiest thing to do. We've worked a lot on the cloud microphysics for the polar regions, and this polar WRF is used extensively in the Antarctic as part of something called the Antarctic Mesoscale Prediction System for the aircraft operations. Okay, just to give you a flavor for the very large domain that we have, there's an enormous amount of data that's going in here. This just is a snapshot at one time of the various types of data going in. For example, you know, the synoptic observations and the airport observations, the METARs, and we use the data stream that goes into the GFS initial conditions. And as we all know, there's tons of observations, both in the ground level and in the free atmosphere at lower latitudes. And as we go northward, the observations thin out, and then we've got this quasi data hole over the Arctic Ocean. The green here are the aircraft reports at this one time, tons over the United States, a fair amount in Western Europe, and sparse in other parts. Okay, we are assimilating the microwave radiances and also the GPS RO refractivity. Okay, so just to give a flavor for the comparison against surface observations, this was done against approximately 5,000 stations scattered. This is the surface variables: 10-meter wind speed, 2-meter temperature, 2-meter dew point, and surface pressure. So this was done for 2000 to 2010 at 3-hour time steps from our reanalysis, and compared to the observations that go into the reanalysis. So we're comparing ERA interim, ASR version 1, that's the 30-kilometer, and ASR V2, which is the 15-kilometer. And basically, we were able to reduce the bias, RMSE, and increase the correlation between the reanalysis and the observations substantially. So the bias is reduced, the RMSE is reduced, and the correlation is. So that's about 2/3 of the variance of wind speed variability of these stations on a 3-hour timescale. And low biases in the temperature, RMSE reduced, and the correlation is high. Similar performance with the 2-meter dew point, and everybody does the surface pressure well. We did a little bit better on the RMSE. ERA 5 would probably look closer to what we have for ASR V2. Okay, we did a comparison for the forecast precipitation, and this was the mean annual total precipitation against the scale. It's kind of a Morse scale, and this is the difference with ERA interim, and the differences are within 10%, plus or minus 10% over the domain. We did a comparison with gauges for 1 year, and the differences in general with ASR V2 and ERA interim are within plus or minus 10% of the corrected gauge measurements. The mid-latitudes were those south of 60, and the polar stations were north of 60, and that's where the gauge corrections really matter. Okay. We also looked at the forecast downward radiation at the surface, and this was for 1 year. And what I can say is that this was versus this satellite product from NASA, series EBAF, if you're familiar with it. And you can see on the top, this is the shortwave bias. So we had a few tens of watts per square meter, generally too much downwelling, not so much in higher latitudes, but certainly somewhat in the middle latitudes. Era interim was generally much closer. Both the long wave that we had and the era interim long wave was similar. So small, quite small biases in the downwelling long wave. So that just indicates that we needed more work to improve the microphysics. Okay, show you a little bit about the, this was a case study of flow down Nares Strait between Ellesmere Island and Greenland. And it's a rather narrow channel, and they get these jet flows or gap flows down this strait. And so you need high resolution to capture that. Hopefully, you see that also in CARRA. You probably do. You have a domain over Greenland. And so this particular case, going to high resolution, double the resolution, showed the jet flow much more reasonably, and a much more complex low pressure system in close to the northwestern tip of Greenland. If you're familiar with this area, this is the North Water Collinear in the wintertime, sets up here at the exit of Nares Strait. So that's one application of topographically forced flow. There was this paper that was led by Kent Moore that appeared in the Quarterly Journal. And once again, we were doing the comparisons with era interim. On the left is the case of barrier wind flow that sets up at times along the southeast coast of Greenland. And as you go to high resolution, era interim, as you remember, was about 80 kilometers. And if you go to 15, you resolve the jet structure of the barrier flow better. And on the right was a case of an easterly tip jet, which happens, you get these westerly and easterly tip jets. Well, this was an easterly case, and much more structure as you go to the higher resolution in ASR V2. That's the reds. Well, this was a comparison against DMI stations on southeast Greenland. And this is how era interim was able to capture the wind speed. And probably because it's significantly higher resolution, in this particular case, ASR did a very, very good job, actually, in capturing the wind speeds at these individual stations. In this easterly tip jet case, the observations from, I'm not sure I can pronounce the name very well, this radiosonde site was in the black, so this low-level jet structure. And of those, in the comparison, so interim ASRV1, ASRV2, and in this particular case, ASR did very well in capturing jet structure. Oops, excuse me. And then this was a dropsonde from out over the ocean. And once again, the jet structure out there was well captured, actually. So a high resolution vertically and horizontally really does help. Okay, polar lows. This was a paper that appeared in Monthly Weather Review by some colleagues of ours from Russia, looking at, this was a particular case and it definitely, even at 30 kilometers, did a significantly better job in capturing the structure and intensity of this one polar locus, as you can see in the satellite image in top left. And compared to some lists of polar locoses, it showed up about twice the amount of polar lows with respect to those shown by era 5 probably looks closer to what would be seen in ASRV1 or ASRV2. Okay, this was a paper that appeared in the Quarterly Journal from Patrick Stoll. And one of the things that they did was to look at the annual polar low hours in a 220 kilometer radius. And this is this scale. On the left was era interim, and on the right is ASRV2 for 2000 to 2016. And you can see that this maximum shows up between Svalbard and Greenland much more prominently in ASRV2. And the seasonal cycle, at the various places is similar. Another thing that's notable is that ASRV2 picks up a lot more polar low activity in the North Pacific, in the Gulf of Alaska, and to the east and west of Kamchatka. Okay. Well, quickly, there's a lot of warming going on in the region of Svalbard and Novaya Zemlya. And this was from our paper in BAMS, so this is 5 years old now. And there was approximately 40% decline in the January sea ice around Novaya Zemlya. So that's what we put in for reanalysis. This is a statistical test. The reduced sea ice cover enhances the sensible and latent heat flux from the ocean. It was ice covered, is now open water, leading to an extreme linear change in 2 meter temperature over 13 years of nearly 13 degrees C. So the temperature really zoomed up in that area. And as a result of the warm temperatures, there was also more, and the increased fluxes, sensible and latent heat fluxes. There was more moisture in the atmosphere. There was more downwelling, long-wave radiation at the surface. These are all trends in downwelling long-wave radiation and 2 meter specific humidity. And there was a significant increased downwind of the precipitation. And these numbers are large in percent per year. And the downwind of where the decrease was because of the counterclockwise circulation over the Arctic. Oh, this is a study that was done. I was a junior author on this paper, but we compared the observations from CloudSat, which of precipitation, and it's not perfect right down to the surface, but anyway, so this was for 2000 to 2007 to 2010 when CloudSat was fully functional. And so this compares the time series of the snowfall rate in millimeters of water equivalent per year for various categories, basically over the, forget exactly where, I think it was north of 70 actually. And of those, unfortunately, CloudSat doesn't work very well over Greenland, at least in the edges of Greenland. So the ASRV2 did a very close fit, actually, over the continental areas. It was the closest to the CloudSat observations over the ocean areas of the in comparison to the other two. So that was really quite a success, actually. And I believe that Era 5 should be fairly similar to what was in ASR v2. All right. So we did this study of the climate extremes over the North American Arctic. And because we have this domain that stretches into the mid-latitudes, we could go into northern part of the US. And this is these performance metrics for the warmest annual temperature. And basically, this compares different reanalyses for ASR v2, NAR, which is the North American Regional Reanalysis, Era 5, MERA 2, and this was an observational-based data set. And things look better the darker the colors are. And basically, I can say that for this particular thing, that ASR v2 in this particular variable looks very similar to Era 5 and significantly better than, for example, MERA 2 with this particular metric, the KGE, that merges correlation, bias, ratio, and relative variation. Okay. So what are we going to do next? We've been thinking about how to proceed. We decided not to extend ASR v2. Things are quite dated. So we're going to try version 3. We're going to start again at 2000 and go to 2026, most likely. We're going to use the NOAA MP land surface model. And the most important thing there is it's a multi-level snow model. And there's a lot of lakes that start to show up at the kind of resolution we're talking about. We're going to go to 9 kilometers from 15. It's the same domain, but we can do this now in one domain. And we saw earlier there were some issues with cloud microphysics. So we need to work on those, and we're going to use this Morrison this microphysics scheme that's available, and with some optimizations. We're going to once again use high horizontal and vertical resolution, an enhanced version of, we're still going to use 3D bar, but an enhanced version. We do want to assimilate the Greenland AWS observations. And we are, like similar to Era 5 and probably Era 6, we use a downscaled land data set driven by the reanalysis. Okay. And the lateral boundary conditions will be either Era 5 or if Era 6 is available. And so, all right. So to summarize then, hopefully on time, it looks like it. We've completed this 15-kilometer ASR v2. It's been available for a little while. You can get it through NCAR, CISL, and ASR v3 is on the way. So some lessons, general lessons learned. Most of these are obvious, but I thought I'd make a list. Some of them are relevant to CARRA and already are well covered by what's going on with CARRA. It's really good to have steady funding. We had funding from 3 different sources, so that's not a problem that you have with Copernicus. You do need dedicated HPC resources to get the CPU cycles that are needed. These are very demanding applications. It really is good to repeat more than once so that you can fix the problems and enhance the physics and generally put in improvements. Engaging with users is very rewarding to identify strengths and weaknesses of the reanalysis, but also to identify unexpected applications. And I didn't have time to show it, but one of the things our reanalysis was used for was to investigate the development and modulation of fires in Arctic regions. High quality data support, you have that through Copernicus. It is required for success of the reanalysis. We had very good cooperation from INCO, and ASR, with its much larger domain, in some ways complementary to and then I'll stop there. Thank you for your attention.